All right. Good morning, everybody. Just to check if everyone can hear and see me wherever you're watching it from. Okay, so we have talked about the concept of polyhedra and the regular polyhedra, which are called the Platonic solids. And we saw their models on the right in the right column here, and hopefully you practiced drawing them a little bit. Now I'll demonstrate to show that in no way does it have to be perfect, and mine won't be at all, but let's build up from the easy ones and see how can we draw these. Oops, it's too big. So let's start with the easy one, the cube. Everyone should be able to draw the cube already. And again, we're just looking for a rough. That is way too long. Let's pretend I'm going to make these mistakes on purpose, like I usually do, just to illustrate that it doesn't have to be perfect. It doesn't have to be perfect in any way. Now, the cube is nice enough without the dotted lines for the back edges, but you can certainly include the dotted lines if you want to. I think it doesn't need them, so you're perfectly fine without them. Cube. Good job.
Cube. Get down step.
Someone has feet.
Cube.
And you're gone. All right. It happens. Next up, let's start with the simple ones, the tetrahedron. Now, whoa, that was supposed to be an H. We're going to talk later about where these names come from. For now, that's the name, the tetrahedron. So the easiest version is not necessarily these ones, although that in the tetrahedron case, it kind of is. You start with a triangle facing the front, and then there are triangles in the back, which you can very easily indicate with the dotted edges that sits behind this front face. Just to check, should I even be doing this, or can everyone draw this perfectly? Did anyone even try? Am I talking to myself? All those things are optional and very possible. The cube doesn't present much of a challenge, but maybe the others will. So next up, in terms of complexity, octahedron. Now, everyone has their own way of, can I not write and talk at the same time? Everyone has their own way of drawing these guys. For me, I noticed that the if I cut it in the middle, I get a square. Now I can make the dotted lines because the back will be. So I can sort of use that square cross section, or if I can do a straight line, as my guide. Then I will put a dot at the top, a dot at the bottom for the top vertex and the bottom vertex. There's going to be an edge towards each corner point of the square. That will be a back one, and that will not. Oh, come on. I'm doing this. I'm doing this on purpose, of course. Deceptively hard because I can't see my hand on this tablet. And then from the bottom one out, that's a back edge, and that is a solid line. And there's your octahedron. This edge got away from me. But it's good enough. It's recognizable. We're aiming for recognizable. That is our goal. Now, this might not be how you do it, but if you are lost and you don't know how to even start, the cross section, the square in the middle, helps me keep track of it. I can probably do better if I do it again. So I have to do, it's like a rhombus. It's a rhombus in the middle when I look at it just as a two-dimensional shape. It's rhombus. But I can make the back and the left side a dotted line because it's going to be a back edge. So let's fade that a little bit with erasing some of it. There we go. Then if I look at my cheat sheet, the octahedron has a top and a bottom edge. It's like sort of like a diamond idea. And then from the top vertex, sorry, not edge, vertex, I have an edge coming down to that middle square, and from the bottom vertex, the edge is coming up from the middle to the middle square. So I'll put a dot. I can put them higher if I want to, not an eraser. Here we go, and maybe over here. Let's use straight lines to help me. You can of course use a ruler even. Okay, hold on. I can't speak and draw the straight line tool apparently. There are two of them. Now the next one is a back one. Then from the bottom one, and the last one is a dotted one again because it's behind. That was a little bit better. Again, not perfect. My bottom vertex was a little too close, but it's recognizable and it doesn't look like any other one, and that's what you're aiming for. When I look at it, is it clearly one of the five? And it doesn't look like any other one, but it doesn't have to be perfect, of course. Just a rough sketch of a three-dimensional object on a flat surface that takes some practice, perhaps. Is everyone comfortable with drawing the first three in terms of complexity, the first three? Any questions so far? We are not in any kind of hurry, so take the time to draw it with me. You can use a ruler, you can use freehand, it doesn't matter. I just like the straight lines were just easier because I can't see my hand. But even the top version of the octahedron was perfectly fine, and I didn't use any straight line tool at all. It just takes some practice. Once you get a method for where to begin, then that definitely helps. And of course, the last ones will not be any easier. Let's go icosahedron. Why do I keep writing a B? Icosahedron. Why is it named an icosahedron? We'll learn that later. Right now we're drawing this, or trying to. And again, the icosahedron, if I have a plan for how to start, that certainly makes things much easier and less wobbly though it's still gonna not look like this computer generated one. So if I look at the icosahedron, I first of all don't want to draw the dotted lines because it's just going to be too messy and that's going to make it unrecognizable. So I just want to draw the edges and faces that I can see, not the back ones. So don't worry about any dotted lines for this one. I see an upside down triangle looking right at me. I'm going to start with that triangle. And again, I'm just going to freehand this so it's not going to be great. Let's make it fairly big. Whoopsie wobbly. There is my triangle. Upside down triangle. Right, looking right at me. Then I'm going to focus on these two lines on the side, on either side, that sit a little higher than the middle triangle. Now I can make it a little bit more interesting by putting one closer than the other one, or a little higher. Oh, come on. Straight line. Hand. Like that. Maybe this one's a little higher. Those are these two straight vertical ones I see on either side. Then from the top two vertices in my front-facing triangle, I'm going to go to either end of those lines. Again, this is just my version. Do whatever version you want, but if you have no idea, this is an option. And then I'll also connect the bottom vertex of the triangle to the bottom of that line. And it's slowly taking shape. Everyone with me so far? Those that are actually needing to have a plan. That if you have your own plan, go right ahead. I'm trying to go slow enough because in the past I know these last two are not easy. Then I'm going to go make a top vertex and it's going to have four lines coming out of it. Not too high. Top vertex, four lines coming out of it. If I can actually connect it. There we go. From the dot, there we go. And to the other one, and to the other one. There we go. Maybe that was a little low. Whatever. And lastly, I have my bottom vertex. Bottom vertex with three lines coming out of it. I won't put it too high. Three lines coming out of it. And there we go. Does it look great? No. Does it look recognizable? Yes. So that is going to be how I attempt a reasonable version of the icosahedron. Of course, it takes some practice. Is everyone good with that one, or should we do it again? Silence means perfect. Then we'll go to the dodecahedron, which is our last one. Scroll up here like so. If I look at that one, this version on the slide here is less than ideal for me because it starts with an upside down and slightly off-centered pentagon, which is perhaps a little difficult. So one option is to just start with a straight-facing pentagon, make it as easy as I can for a start. Then I want to draw little lines coming out of each of those vertices. I'm trying to simplify this. It's not going to look that great. And then in between those lines, across from every edge of my starting pentagon, not too high, I'm going to draw a dot in the center a little higher up. Not a lot, a little bit. And then I'm going to connect the dot to the tops of each line. And there's a good enough version of my dodecahedron. Now, of course, the length of the lines and the positions of the dots and the exact symmetry of my original pentagon will affect everything. So you can experiment. Well, what if I make my pentagon a little off center and position these lines? Maybe one is a little higher, longer than the other ones. Maybe these ones are short. What happens then if I put these a little higher? I can't make them that high. Like so maybe. And these ones a little short, close in. What happens then? So it takes some experimentation, I suppose. This line was too long. Take some experimentation and see how can I make it this angled version and make it nice and round. The lines you see there are not all the same length, but depends on how much artistic skill it depends on how much artistic skill you have, how much effort you want to put into this. It's recognizable. I see the pentagon. There's only one with a pentagon face, so we're aiming for recognizable and nothing else. All right, so in case you're wondering, yes, you have to be able to draw each of the 5 Platonic solids. So do practice that. Now we want to fill in this sheet where we want to know for each Platonic solid what are all its properties. How many faces does it have? How many vertices does it have? How many edges does it have? And everything there is to know about the Platonic solids. Let me just make this as big as possible. That should be good. I think my pen is way too big. The sheet is on my screen right now. I made it for the lecture, which is where you benefit by showing up. But you can also pause the video later and take a screenshot or something, or go back in the video now. Whatever works for you. The point is, this three columns, faces, vertices, and edges are what we want to fill in. But in order to help my discussion, I need some other stuff to have something to look at. We don't need to really draw this many triangles. It just helps me explain how we get these last 3 columns. So, first up, tetrahedron. Tetrahedron is number 1. My pen is still way too big. Is that better? Yeah, that's way better. Okay, so a tetrahedron consists of 4 triangle faces. Here are the 4 faces, as if I sort of cut them out. I cut the polyhedron and I broke it up and I just arrange and lay out all the faces. Or I can pretend that here are all the faces. I now have to glue them together to make the tetrahedron. Okay, so I have to glue 4 of these faces, these triangles together to create this three-dimensional shape. So the faces are 4 that I can see on my picture, and I can also just memorize it. But in order to get the total number of vertices and total number of edges, I prefer calculation instead of blind memorization. So vertices first. Forget about the edges, vertices. To help me understand how to calculate that, I'm going to think of gluing these triangles together to make the polyhedron. I have 4 triangles. So before the gluing, they each contribute 3 vertices because it's a triangle. Each one contributes 3 of these vertices. There are 4 triangles, 3 times 4, 4 times 3. So my total vertex contribution is 12. It's very important as we go, you stop me immediately when you're not sure about anything. Anything. This is super important. Now, many people do go the memorization route. I don't like that. I'd rather understand what I'm doing. And if I panic, memorization fails is always the first thing to fail. So 12 individual vertex contributions before I start gluing. Okay. Now, when I glue it together to make the tetrahedron, 3 triangle faces come together to make a vertex of the tetrahedron. So I'm going to take this 12 contribution, and I'm going to have to, let's do it like this. I'm going to have to divide it by 3 because they now form a single vertex. Every 3 of them are coming together at the top here, for example, to make a vertex of the tetrahedron. So because 12 divided by 3 is 4, there are 4 vertices in my tetrahedron, which the sketch isn't hard to draw and read that 4 off. I have a top one and I have 3 at the bottom, 4 vertices. But later on it gets a little tricky, so a calculation route is beneficial later on. Right now I can just count them. 1, 2, 3, 4. Sure. But if I look at how the faces come together to make the three-dimensional shape, I can get the 4 in a different way. Okay. For the edges, I'm going to do the same thing. Let's make some color. Let's take some color. If I look at a triangle, each triangle contributes 3 edges. So the total edge contribution will again be 12 because each triangle contributes 3 edges. There are 4 of them being glued together. 3 times 4 is 12. But when I glue them together to make the tetrahedron, 2 triangle faces come together to make a single edge in the tetrahedron. So I'm going to have to see the original edge contributions now coming in groups of 2 to form an edge in my tetrahedron. So I'll have to break this up into groups of 2, and I'll therefore get 6 edges for my tetrahedron. Now again, this seems like overkill. Because the tetrahedron is so easy to look at, I can count 1, 2, 3 edges going to the top vertex, 1, 2, 3 at the bottom. So yeah, obviously 6. Yeah, but later on it's not as obvious. So I want to come up with an alternative way to get the vertices and edge numbers when the diagram gets messy and tricky to count directly from that diagram. So I have 4 faces in the tetrahedron, 4 vertices, and 6 edges. Is everyone happy with the tetrahedron? I know when we do this, it's often stunned silence. You're just awed and amazed at how awesome Platonic solids are. You don't know what to say. All right, no one is saying anything, so I guess I will continue. Let's make the vertices blue. But first, octahedron is next. My second one here. I can, I have to remember the faces as 8. 4 at the top, 4 at the bottom, 8 faces in total. So now let's go blue for the vertices. All right. So now again, I have 8 triangles that need to be glued together to form this octahedron. When I look, because they're triangles, each one is going to contribute 3 vertices. And there are 8 of them, so 8 times 3. So my total vertex contribution is now 24. But when I glue them together to form the octahedron, 4 triangles come together to make a single vertex in the octahedron. So I'm going to divide this total vertex contribution by 4 to get the number of vertices as 6. Now again, not the hardest thing because the little diagram, the little picture is easy enough to count the 6. I have 4 from that cross-section square, 1 at the top, 1 at the bottom, so 6. For the number of edges, we'll go pink. Now I have these triangles contributing each 3 edges. There are 8 of them, so 8 times 3. So again, a total edge contribution of 24. But when these triangles are glued together to make the octahedron, 2 of them come together to make an edge of the octahedron. So I'm going to be dividing that by 2 to get the total number of edges as 12. I would just like some confirmation that everyone can still hear me and that everyone is following what we're doing. In the past, this was not the easiest thing to follow for everyone, so just want to be sure. Now, these first ones are easy because I can just use my diagram. but I'm trying to get ready for the ones that have more tricky and complicated diagrams where I can't trust my own. Next up, the icosahedron, if I finish my triangle faces. All right, so now for the icosahedron, I have to remember, and we're going to come up with how to remember that I have 20 faces. 20 faces in the icosahedron. When I now try and count the number of vertices, let's go blue. I have, let's do it over here, a triangle again, contributing 3 vertices each. I have 20 of them. 20 times 3 gives me a total vertex contribution of 60. When I glue them together to make the icosahedron, 5 triangles come together to make a single vertex. So I therefore am going to have the 60 in groups of 5. How many groups? That's division. That is an ugly 5. That is not better in any way, but I'm going to stick with it. I get 12 vertices. Much more difficult to count because there are a bunch at the back. So this is where I'm a little less comfortable looking at the diagram, especially if I have to make that diagram myself. Imagine trying to count the vertices on this guy. I'm going to make a mistake. So now the calculation route is a little bit safer if I understand how the faces come together to make the shape. Next up, we have each triangle contributing 3 edges. That gives me 20 triangles, 3 edges, giving me 60 as a total edge contribution again. But just like always, these faces are glued together and 2 of them will make a single edge. So they come in groups of 2, whoops, all the way through. How many groups? 30. So there are 30 edges in the icosahedron. If you like the challenge, go and count them, but that's not a challenge that is worth my time and effort. Icosahedron, done. Oops, pink. 2. The faces always come together, groups of 2, to make an edge. But to make the vertices, that number changes. So, regardless of how perfect I can draw the icosahedron, even if I look at this version, there's so many at the back, I I can't count the edges with confidence at all. Next up, our familiar, whoops, not pink, much more familiar cube. I have how many faces? Well, the cube, I can imagine the cube, 4 around, 1 at the top, 1 at the bottom, 6 faces. Now, vertices. Again, not necessary because I can draw a very accurate looking cube, count them, but how else can we do it? The square faces each contribute 4 vertices. I have 6 of them, so my total vertex contribution is 24. To make the cube, 3 squares come together to make a vertex. So I'm going to count the number of groups when they come in groups of 3, and I therefore get 8 vertices, which I could have counted, I know, 4 at the top, 4 at the bottom, but you have multiple options here for how to get that 8. So the only thing I memorize is the number of faces and how the faces come together to make the shape. Everything else is understanding. And I need to minimize how much I memorize because those things easily get lost. Next up, the edges. I have 4 edges that each square contributes. I have 6 of them. Again, 24 edge contributions. Like always, 2 faces come together to form an edge in my square, in my cube. So I'm going to divide that by 2 to get the total number of edges of the cube as 12, which of course you can count, but this way is not slower in any way. So it really depends on how much you can trust your sketch. One more, but now I have to scroll up, so I have to remember what each of these columns represent. I can write them at the bottom here. Faces, vertices, edges. All right, last up. I cannot draw a 5 today. The dodecahedron. Dodecahedron has 12 faces. And probably tomorrow we will understand why I just know the 12. But right now you are going to have to memorize it. But I don't memorize anything other than the number of faces and how those faces, pentagons in this case, come together to make the dodecahedron. All right, vertices. So I have, let's do this one, 5 vertices because the faces are pentagons. That each one contributes 5 vertices before they're glued. I have 12 of them, so my total vertex contribution is 60. But when I glue them, 3 of the pentagons come together. Oh, I shouldn't have done pink. The vertices were blue. Back it up. Blue vertices. That's my mistake. I'm sorry. Feel free to leave hateful comments. 12 pentagons, 5 each, 60 for the total vertex contribution. When the faces are glued, 3 of them come together at a point to make a vertex in my dodecahedron. So I'm going to have to divide by 3. They come in groups of 3, that is division. 60 divided by 3, I have 20 vertices. For the edges, let's do this one. I have, because they're pentagon faces, 5 edges that each one contributes to the dodecahedron. So I have now 12. I have 12 pentagons, 5 edges each, so 60 again. But when the faces come together to form edges, only 2 faces are needed to make an edge in the dodecahedron. I therefore divide the edge contribution by 2, like always. Stop it. I can't get the black. Oh, I'm black. Okay, good. Therefore, I have 30 edges in the dodecahedron. If you like the challenge, go right ahead and count them. I'm not going to. All right. That is how we do it. Now, if I look back, I want to find a relationship, a link between faces, vertices, and edges. Some link between them that is always true. And I'm going to go a little bigger with my pen, this pen. And I'm going to go green. Let's go green. What is the link between the vertices, the faces, the edges that always works regardless of which Platonic solid I'm looking at? They're all even numbers, yes, good. But I'm looking at a link between them. How are they combined? Maybe some are combined to create the other number. There's some arithmetic link between them. Does anyone have any idea what arithmetic could be linking them? So I'll give you a clue. What if I add the number of faces and the number of vertices? Then, no, there's different ways to write this, just to match the slides. If I add the number of faces and the number of vertices, that answer is always 2 more than the number of edges. If I add the number of vertices and faces for the octahedron, that's 2 more than the number of edges. What you said was right. Just to match with the slides, I'm going to write it this way. Add the number of faces and the number of vertices, and it's 2 more than the number of edges. 2 more, 2 more. So let's go back to my slides. Not that slide, this slide. So just a side note, um, when the Greeks discovered that there are only 5 Platonic solids, they thought, oh, there had to be some higher meaning to this, some mystical significance. So they associated each of the Platonic solids with an element in nature. Cube was earth, the tetrahedron represented fire, icosahedron represented water, the octahedron represented air, and then they had a fifth one. They had to do something with it. The dodecahedron represented the all-encompassing universe. As an interesting note, depending on the culture, they try and attach meaning to these things. What's interesting is that these Platonic solids occur in nature. It's a little perhaps too close to home, but a lot of viruses have an icosahedral shape. In the ocean, there's some living organisms that have uh, Platonic solid shapes. Now a little curvy perhaps, but these shapes, so, people think that there's some optimal energy minimization happening when um, your design are uh, your design is sort of fitting one of these shapes. There's some optimal uh, thing happening, but no one exactly knows why these shapes occur naturally. Anyway, we've explored the number of faces and edges and vertices in the Platonic solids, and we get this bottom equation that's called Euler's formula. One of the greatest mathematicians ever looked at this, and it's part of a much larger equation that relates vertices, faces, and edges. In our case, for the Platonic solids, we have the number of vertices, the number of faces is always the number of edges plus 2. But that makes my life a lot easier when you think about it. That means that if I have a way to find, or if I remember two of the three, then I can find the other one by way of Euler's formula. I don't need to calculate them all or memorize them all. And the edges to me, that is the more difficult number. Let me just go back to my black here. So if I remember the number of faces, I can find the number of vertices, then the number of edges is always 2 less than the faces and the vertices added together. So I don't have to do a whole count for every one of these three numbers. If I have any two of them, then the other one is automatic by way of this formula. Or if for some reason I have the number of faces and the number of edges, then I can use this equation to find the number of vertices. I don't have to recount uh, using a more complicated um, argument. I can just use Euler's formula to find the missing one of the three. I just need to know two of the three. So it does make my life a little simpler using Euler's formula that the number of faces plus the number of vertices equals the edges plus 2, or whichever version you prefer. We will pause that here for now and look at where the names come from tomorrow. Any last questions before we switch to office hours? All right, that will be it for the lecture.